Our first session is by William Corbett, KTA Tater. Bill is the Chief Operations Officer for KTA Tater, where he has worked for 39 years. He has an AD in Business Administration from Robert Morris University, multiple certifications from SSPC and NACE, and is a course instructor for both SSPC and KTA, and is a recipient of multiple awards from SSPC and ASTM, and the chair of the SSPC Dry Film Thickness Committee and Education and Certification Committee. His presentation will highlight the electronic instrumentation that can support in-process inspection of railcar lining applications. So, Bill?
Okay. Don't anybody move, because somebody moves, this laptop could go over the edge, all right? It's like the golf ball on the edge of the hole. It's about to go over. It should be fine. Can everybody hear me okay? Yes. All right. I'm going to move away a little bit from the microphone, if that's okay. If I get a little bit soft, I'll make sure I stand over a little closer there. So what I wanted to talk about today was the importance of verifying quality during surface preparation and coating application or lining installation in tank cars, although it could be interior or exterior coating or lining work. And, you know, the primary reason we do that is to control corrosion, but we also want to have a barrier between whatever product we're hauling in those tank cars or hopper cars and the steel itself. So we actually have a couple of goals we're trying to achieve there. And frequently, car shops will have quality control personnel to verify that those coatings and linings are being installed properly. But anytime you invoke quality, sometimes that interferes with, well, frequently it interferes with production, because we have to stop and we have to check the quality of work that's done before we go on to step 2 and step 3 and so forth. But we can use some newer technology instruments to, you know, limit that productivity interference. And that's really what I'm going to talk about today, is some of the advantages of using newer instrumentation to be able to do that. But I'm also going to revisit some old, tried and true ways to do quality control in the shop that are unrelated to instrumentation, because I don't want to just focus on instrumentation. Also, I did bring a kit of instruments that are sitting over on that table over there. I'm going to be here all the way through this session, so at the very end, at 3 o'clock, when we finish up with everybody's presentation, if anybody wants to come over and try out some of that stuff on some test plates or just take a look at it, that will be sitting there until, I guess, about 3:30 this afternoon. So if you want to take advantage of that, it's over there. So what's the big deal? Why do we have to verify quality? Well, there's opportunity for coating failure if we don't. We could end up with accelerated corrosion depending on what's being hauled, what the product is being hauled. We could also end up with product contamination. So it's very important that these coatings stay adhered and do their job. If we don't verify quality throughout that process, it doesn't mean the coating is going to fail, but it's at a higher risk for coating failure if we don't verify the quality. So when we talk about verifying quality, there's 3 big areas that we look at. We look at pre-surface preparation, then surface preparation, and the installation of that lining or coating system. And each one of those has its own inspection checkpoints associated with it, and you can see those on the slides. And really, that's going to be my focus for the next 20 minutes or so, and hopefully we're going to have some time for questions at the end that I'll be able to take on here. So the first checkpoint I want to talk about is verifying that any grease, oil, lubricants, or whatever was on the surface have been adequately removed. There's no instrumentation here. All the instrumentation is maybe a rag or maybe a black light to be able to fluoresce the oil or grease on the surface. I guess what's most important is that most tank car preparations are done by abrasive blast cleaning. And many of the abrasive blast cleaning standards, in fact nearly all of them, automatically invoke solvent cleaning to remove grease, oil, lubricants, whatever process had been performed prior to surface preparation. So for example, if your specification says to prepare the surface to a commercial blast, a near white blast, a white metal blast in accordance with SSPC or NACE standards, this is automatically invoked. Whether your spec has it in there or not is moot. SSPC and NACE require it. Okay, and that's an important point. In-process cars that are being rehabilitated or whatever the terminology is, if there has been product in there that might have contributed to soluble salt contamination on the steel surface, we want to be able to detect those and, if necessary, remove them. And there's a couple of different ways we can do that. We can actually extract a sample from the surface and analyze it for whatever salt we're interested in. It might be chlorides, it might be sulfates, it might be nitrates, it could be ferrous ions, whatever product contamination potential there might be there. All right? What some people are looking at doing is they're not being ion specific. They're just simply extracting a sample from the surface using distilled water and immediately depositing it onto a conductivity meter because they really don't care what salt it is. If it's at a high enough level, they know they're going to have to do some pressure washing or water jetting to reduce that surface concentration down. It doesn't really matter whether it's sulfates or chlorides or what the salt is. So we can do non-ion specific testing or we can do ion specific testing if we really want to know what the bad actor is. This again doesn't really involve any instrumentation, but it's another important checkpoint. If we're going to use compressed air to abrasive blast clean with, or when we use compressed air to abrasive blast clean with, or if we're going to use that compressed air to blow the surface down to remove the dust from the surface, we have to make sure that compressed air is clean and dry. How do we do that? It's called a blotter test or a compressed air cleanliness test. There's an ASTM standard for it that's listed up there. There's the potential that the compressed air will have water and maybe even oil contamination in it. We need to make sure the extractors or the separators that are in line are doing their job, or removing those materials before we exhaust the compressed air on the surface or combine it with the abrasive. Once again, even if your specification doesn't specifically require this test, the SSPC and NACE surface cleanliness standards require the use of clean, dry, compressed air. How do you determine that? You do a test like this. All right? And simply exhausting the compressed air for about a minute onto a collector and examining that collector for oil and water is all you do essentially. The next automatic or indirect requirement, automatic communicates a little bit better, is making sure that our abrasive is clean. Whether it's new abrasive or whether we are reusing an abrasive like steel grit or steel shot, again, SSPC standards, the cleanliness standards for abrasive blast cleaning, require the abrasive to be verified for cleanliness. They require that clean abrasive be used. How do we determine that? What do we mean by clean? Well, there's two tests. The first test is the top one. We're checking for oil contamination on the abrasive. By taking a sample of the abrasive and combining it with regular old tap water is fine. Shaking it up for about a minute and then letting it settle, and then looking for an oil slick on top of the water. Very simple test to do, and it's very routine. We have found that a lot of folks are doing that test pretty routinely. What they're not checking the abrasive for is residual conductivity or water-soluble contamination that might be on the abrasive. Because we remove a coating material or a lining material, and in the process we've contaminated our abrasive. And if we're going to reuse that abrasive over and over again, we could potentially contaminate even clean surfaces. So there's an ASTM test for that. It's ASTM D4940, and we take a known volume of abrasive and a known volume of distilled water or deionized water and combine them and do an extraction. And then we filter off that water and then measure the conductivity of the extract, not of the abrasive itself, but whatever came off the abrasive and solubilized in the water. All right? And the kit, a kit that has all the equipment to do that is shown on the bottom there. So we're not supposed to have any visible oil on the top surface of the water. We are allowed to have some conductivity to the abrasive. So the maximum amount of conductivity is 1,000. For below 1,000, SSPC says that abrasive is considered clean. If it's over 1,000, we have an issue. Okay, I've been talking about these surface cleanliness standards. Here's the 5 that SSPC and NACES are joint standards between the two organizations. So it's one definition, one set of definitions for each of these. It's not two different standards for each one. The ones that we see most commonly specified are commercial glass, which is SSPC SP6, and near white glass, SSPC SP10 or NACE2, and then SP5, NACE1, which is the white metal glass. Those are the 3 more common ones, and then there's some others for the maintenance industry. These standards, back up, these standards all have definitions as to how much material or how much staining can remain on the surface. Commercial glass allows up to 33% staining, and near white glass up to 5% staining. White metal glass, you can't have any staining. Well, what does that look like? What does 5% staining look like? It's very difficult, it's judgment, it's subjective. So what SSPC did back in the late 1980s, early 90s, is they created a series of visual guides that contain pictures of what the post-blast is supposed to look like, because the picture's worth 1,000 words. We can argue all day about what 5% is or what 33% is, but if we have a picture, we can all put it on the same page. So what SSPC did is they came up with these visual guides. Because my time is limited here, I'm only going to focus on SSPC Biz 1, which is for dry abrasive glass cleaning. And basically all you're going to do is you're going to choose the representative initial condition of the steel. For example, let's say it's rusted and pitted. Look at your specification, it requires a near white glass. So we're going to look at this picture in the visual guide and say, does my surface look like this or better? If it does, we're good to go. If it's less than or greater amount of staining or less quality, then we have to do additional work. Blast cleaning not only cleans the surface, but it increases the surface area. So we create a surface profile in the steel. And essentially, we want to be able to measure the depth of the surface profile because our specification typically is going to have a minimum and a maximum surface profile, and we have to stay in that range. So how do we determine that? We can't visually determine whether or not we've got the correct profile. We actually have to measure it. Too much surface profile, we can have pinpoint rusting. And too much surface profile and correspondingly not enough lining or paint on the surface. But if we don't have enough surface profile, we can have adhesion problems. All right? So we need to establish that range, and we need to prove that we've met that range. ASTM D4417 is a standard for measuring surface profile. It tells us how to measure profile. It doesn't tell us what it should be. It doesn't tell us how many areas to check. It just says this is how you do it. It describes 3 methods. We're only going to talk about 2 here today. The depth micrometer, method B, and then the replicate, method C. Those are the most common ones. National Association of Pros Engineers also has a standard, SP0287, which is the same as method C in the ASTM standards, the replicate method. And then SSPC PA17 doesn't talk about how to measure surface profile. What it focuses on is how many areas do you check? So if I have glass at the inside of this tank car, am I supposed to check 1 area, 50 areas, 3 areas? What am I supposed to check? PA17 gives us some guidance there. That's a relatively new standard, by the way. It's probably been out about 6 or 7 years. Method B is called a depth micrometer. And what we're doing here is we are actually taking pinpoint measurements of the surface profile. I don't know if you can see it from where you're sitting at, but at the base of the gauge, there's a 60-degree cone-shaped point coming out of the bottom. The theory is it goes into the valley of the profile, the base of the instrument sits on a piece. That depth or distance is reflected on the gauge in either mils or microns, whatever you prefer. What ASTM says, you're supposed to take 10 readings per area. It doesn't say how many areas. When you choose an area, you're supposed to take 10 readings. It sounds like a lot. You get about 10 readings in about, 12 or 15 seconds with this gauge. You don't have to write them down. The gauge will memorize them for you. Remember I said things, we can speed up inspection by not having to record information as we're gathering it. The gauges do that now for us. And of course, we have to verify zero before we use it, and they have a glass plate you can use to check zero with. And again, you can upload that information to the cloud. You can download it to a printer. Once you get all the information, it can be removed that way. Side. So basically, after removing the paper backing, we attach the tape to the surface and literally burnish the tape with the burnishing tool. And what that does essentially is it creates a mirror image of the surface profile in the foam that's on the back side of the tape. So you're creating an impression of the surface profile. Once we create that impression, we remove the tape from the surface and we have a choice. We can put it in a spring-loaded micrometer that gives us the reading in mils, or we can insert that tape in what's called a replica tape reader that will read the depth of the surface profile, store that information, which can then be uploaded to software or downloaded to a printer, whichever is preferred. Now, PA17 says, okay, you're going to use the replica tape, you're going to take 2 readings per area. You're going to use the depth micrometer, you're going to take 10 readings per area. Now, how many areas are you supposed to check? This is where PA17 kicks in. And it says for whatever was blast cleaned in a shift, in a work shift, you check a minimum of 3 6-inch by 6-inch locations. So in each one of these locations, if we were using the depth micrometer, we'd be taking 10 readings, so we've got a total of 30 readings here. It's a minimum. We're using replica tape, 3 areas times 2 pieces of tape would be 6 readings. And again, that's for the amount of surfaces that was prepared during the shift, essentially. All right, and then our final surface preparation step is to make sure that we are not going to put our coating or lining system over dust. So we have to make sure that we either do a blow down or vacuum or a brush off or whatever the procedure is, but ultimately we want to reduce that dust down. We're not going to be able to have it be dust free. That means you can't have a piece of dust anywhere. That's not going to happen. But we want to remove most of the dust so we don't have an adhesion interfering material on the surface. That can be expected either visually by swiping, a gloved hand across the surface and see if you see a mark on the steel, or we can use an ISO method. Now the ISO method can only be used if it's in the specification, because the specification is going to have to give you an acceptance criterion, 1, 2, 3, 4, or 5. But basically you take a clear piece of tape, put it on the blast clean steel after the dust has been removed by brush off, blow down, or whatever, and then ultimately after you put that piece of tape on the surface, transfer it over to a piece of white paper or white backing of some type, and rate the quantity of dust you see on there. So if your specification said dust quantity rating of 3 or less, you know what's acceptable. Unfortunately, ISO doesn't tell you how many pieces of tape to use. They just tell you how to do the test. So what frequency, that all has to be established up front. All right. That's essentially done with surface preparation. Now we're going to move over to some things to look at as far as lining application or coating application is concerned. First one is measuring the prevailing conditions of temperature and humidity and so forth. This is very important because we have to be able to comply with the coating manufacturer's minimum and maximum temperatures and relative humidities. And we also have to make sure that we don't have a dew point surface temperature problem as well. So these conditions should be measured ideally before we start mixing the coating or lining material, if it's a multi-component material, and then throughout the process as well. Now, these whirling psychrometers, I did a little research on these when I was doing a talk for NACE a few years ago and discovered that whirling or swing psychrometers actually date back to the 1800s. So this is really, really old stuff, but it's still used today because it's convenient, it's inexpensive, and people understand how it works. It's the rate of evaporation of water from a little wick around the thermometer. It makes sense to people, all right? And then we have the psychrometric charts that date back to the 1940s for looking up the humidity and dew point temperature, all right? So that's all well and good, but it takes time. Now we have these digital psychrometers where you power up, let them stabilize, and then you can read the information directly from the display. There's no lookup tables, there's nothing like that. You don't have to worry about changes in barometric pressure. That's all taken care of. And you can see that it's all displayed up there, and then there's auto logging abilities. So you can have the machine taking measurements even when you're not there. It does have audio and visual alarms, and there's also an infrared surface temperature probe now that goes up a lot higher in temperature, and I'll talk about that in a minute. So think about this. Let's say that you have to cure a lining system overnight, and you want to be able to monitor those temperatures, but not have somebody do it. You can actually have the device taking those temperatures and feeding the information, as long as you have internet access, to a computer, to a tablet, to a cell phone, and giving you information. You can have alarms go off if it goes outside of certain temperature ranges. There's a lot of capability with these new types of gauges that rail shops can take advantage of. And of course, we're also interested in surface temperature, and there's different ways to measure the surface temperature, from simple dial tech thermometers that again are decades old, to more of the thermocouple or non-contact infrared. They all have different temperature ranges that are available. If you need to go up pretty high, some of the infrared ones do offer that technology. White film thickness, something we have measured for, again, decades and decades. This isn't really a quality control checkpoint. This is more of an applicator's tool to assess whether or not they've got the correct material flow, spray pass, rate, overlaps that they need to achieve the right thickness. Ultimately, what we care about is the dry film thickness. This is a means to an end. But using wet film thickness gauges properly and not overusing them. You know, the aluminum ones that many folks use, aluminum's very soft. It won't last very long, and you'll find out you're going to be getting incorrect wet film thicknesses over time if you outuse those. Or overuse them, I should say. Measuring dry film thickness, something that we all are pretty familiar with probably, and it's interesting to me that as chair of the SFPC committee on dry film thickness, taking a dry film thickness measurement with an electronic gauge is remarkably simple. But it's everything else that gets really, really involved. How many readings do I take? How do I make sure this gauge is even working properly first? Okay? So really that's the basis for this ASTM standard and the SSPC standards, to make sure these gauges can be used properly. I'm not going to get into the scope too much here. You guys can read that for yourself. But basically what the PA2 standard does, and PA's paint application standard number 2, is it gives us a lot of good direction on how to make sure our gauge is working right, and then how many readings to take. There are 9 non-mandatory appendices, and then there's one coming up which may have applications for tank cars, and that's using scanning probes on the surface. That's going to be Appendix 10. That should be out this year. Right? Type 1 gauges, magnetic pull-off gauges, have been essentially replaced by the Type 2 gauges because the data can be collected a lot faster, stored, and downloaded or uploaded without writing anything down. Big advantage in productivity with inspection. As far as gauge use, the gauge has to be calibrated. Typically that's done by the gauge manufacturer or an authorized service center, and usually it's an annual requirement. Verification of accuracy is done with every period of use. So this might be a daily event. You're going to verify the gauge is working properly by checking it on a set of certified coded standards and making sure the gauge can measure properly on a known standard. But remember, we're not putting the paint over or the lining system over smooth steel. We're putting it over a roughened surface. So we have to compensate for that. And so we do that by using measured shims or certified shims and place those on the blast clean steel. Adjust our gauge to match that shim. That way we're only recognizing the amount of coating that's sitting on the piece of the profile. And that's usually what is being specified by the manufacturer or the owner. And then how many readings we take, SSPC PA2 gets into a lot of detail there as well. Again, if this were a formal training class, I'd be going into a lot more depth there. It's just kind of an awareness type thing. But this is the number of spot measurements, the number of area measurements, and the number of gauge readings you would take, and it's all based on square footage of coated surface. Okay. And there's the criteria, less than 300, 300 to 1,000 square feet, and then over 1,000 square feet of coated surface. How many areas you check. In each area, you're always taking 5 spot measurements, and you're always taking at least 3 gauge readings. And then SSPCPA2 has actually established some thresholds on how far out of spec the spot measurements are allowed to be and still be acceptable. Level 3 up there, which is in red, is the default. Anything above there is more restrictive. Anything below 3, like 4 and 5, are less restrictive. So the owner, again, has a lot of flexibility. They can specify exactly how tight the tolerances they want to be. This is all part of PA2. If you don't specify a restriction level, it goes to the default, which is level 3. Right? And then to finish this up here, I'm going to finish up really fast. Holidays and pinhole detection, we want to make sure that our lining system doesn't have pinholes and holidays in. A holiday's a skip or a miss. Pinhole's a tiny void, of course, because that could end up with product contamination, corrosion, and so forth. So we can either do low voltage or high voltage holiday detection. Low voltage is typically less than 20 mils. High voltage is typically over 20 mils. With high voltage detection, it's really important that you calculate the voltage setting. It's a very simple calculation. All you have to do is take the square root of the coating thickness, the square root of the lining thickness, and multiply it by a constant. It's either going to be 525 or 1250, depending on whether you're below or above 40 mils. The example I have on the next slide is a 36 mil lining system, just because the math is easy. Square root of 36 is 6. I'm going to multiply that by 525, because I'm less than 40 mils. I only have a 36 mil lining. That tells me that my test voltage for high voltage should be about 3,150 volts, or 3.2 kilovolt. Okay? I can set my detector to make sure I'm not going to exceed the dielectric strength of the lining, but still get a good detection if I do a pinhole. Now, NACE also has some tables where they have what they call suggested voltage settings, but they establish a range. And you can see 20 to 40 mils, they're suggesting 3,000 volts. Well, for 36 mils, we have about 3,150. So the range is probably okay, but you're better off not going with suggested voltage settings, but actually calculating it. The calculation is in the ASTM standard, E5162. The last thing I want to mention real quickly is hardness, making sure that if we have a cured lining system, that we've achieved the hardness that we need to before we put that lining in service. For thin films, we might use pencil hardness, which is D3363, not a very precise method. Calibrated pencils, traceable pencils, are getting extremely hard to get. No one uses drafting pencils anymore. But it's basically different hardnesses of lead, and you attempt to gouge the lead into the lining system. If it does gouge, it's not ready. If it doesn't gouge and the lead actually gives way, it means the lining is cured. Okay? But again, the manufacturer's going to have to give you that pencil number. They might say, you want to achieve a 3H, you want to achieve a 4H hardness before it's ready to go. And you can test that way. For thicker film systems, we can use either a Shore D hardness tester or a Barcode hardness tester. For many, many years, these were both analog. You had to take readings and write it down, take readings and write them down. Now they put data processors in here so it can all be recorded and again, uploaded or downloaded depending on your preference. So that's just a real quick overview of some quality aspects and how this new technology can still maintain quality, but we can do our inspections a lot faster because we're going to store data in gauges rather than writing everything down in a book and transferring it over to reports later. Okay. All right, thank you.
Thanks, Bill.